Hello, everyone. My name is Noah Wren, and I'm part of FRC Team 2202 Beast Robotics, where I'm one of the two co-captains. Additionally, I'm also on the First Wisconsin Student Board of Directors, and the goal of the student board is to be to help spread FIRST all across the state, and specifically make sure that all students in Wisconsin who are interested in STEM and interested in FIRST have the opportunity and have an equal opportunity to be able to be competitive in the FIRST environment and to be able to enhance their STEM and soft skills. With that being said, one of the key things that drives people away from FIRST is the steep learning curve that they see in robotics. Specifically related to software on the FRC side, it's a really steep learning curve to be able to really get into that. And that's what the XRP bot helps with, is it helps to kind of lessen that learning curve by being a much more simplified version of the actual robot. And thus, since I've already recorded the first session, this is now the second and final formal training session in relation to this. And this one is going to be more on the software side. So with that being said, let's jump right into this presentation. So let me share my screen. And yeah, so for those of you who saw the first YouTube video or were there for the first webinar, this is the same slideshow. And for those of you who don't have the link, it's going to be tinyurl.com/xrp-demo-wi in case you want to follow along today or you're interested in the first video. And in the first video or webinar rather, what we did is we went over all the different steps to putting the actual XRP bot together, went over some basic information about it, and also connected it to the computer so that it now appears as a Wi-Fi network. With that being said, I want to welcome everybody in today to this webinar and thank you for attending. So quickly for our objectives and a quick overview, this is probably going to be much shorter than the first 90-minute webinar simply because it's just me already having done everything, kind of going over the code and showing different videos as opposed to a live webinar where we're waiting for everybody to also work along with what I'm presenting. So hopefully this will be around 30 to 40 minutes, a shorter time frame. But of course, when you're actually watching the video, pause whenever you need to and do all of that to ensure you get the best experience. So with that being said, quickly around the 5-minute overview, which I've already been jumping into kind of as I've been talking. One thing to mention with the 5-minute overview is the format of this specific webinar or video is that since if I were to connect to the actual XRP bot, which I need to do in order to actually present, what this means is that I would have to be connected off of the Wi-Fi network, and thus I couldn't really record on Microsoft Teams, unfortunately. If we wait a sec, you can see in the Wi-Fi networks, you need to connect to the XRP bot. So that isn't possible. So the format is basically, there will be these like videos that I show that I've pre-recorded that go along with the code that I've done instead of actually doing it live, since that just isn't possible. Since as we see here, once this loads, I would need to connect to the XRP bot as my Wi-Fi network, and I can record the Teams meeting. But I'll still explain all of the code and all of that. That's just a quick note to mention about how you'll actually see for this. Yeah. So next, we'll first do a really quick intro on like movement overall and network tables, and that'll also help us get into the format, get used to the format. After this, autonomous and a quick debug that you can perform in relation to network tables, just a really quick example. And then after that, we'll go into the ARM and the servo specifically, which will take around 7 minutes. You can see all the times are listed there, but these are just estimates. In reality, it will vary a ton. And then finally, it's going to be the distance sensor and putting everything together and going over the distance sensor. And then we'll go over possible next steps that you can take. Yeah, with that being said, let's jump right into the code. So let's see water. One quick thing that I should mention is in relation to the code, what I'm first going to go over is some of the basic files that you'll see in essentially every FRC program. So first, a really high-level overview is robot container. Basically, always see this. This is where you'll bind your buttons or bind your commands to buttons. So like you create your commands and you bind them to buttons in robot container, which is where you actually run like the buttons you press on your controller. One quick thing to mention, I know that a lot of you might already have this knowledge, but I'm just going to do the highest level overview possible just in case. So kind of quickly running through just like a high level overview, super quick through this file. All we're doing is creating the drivetrain, creating the ARM, creating the XRP, all the different motors that we're going to use. Here we're just configuring the controller, configure the bindings. Otherwise, here you can see is where we actually create our commands. So here we're saying the joystick button. This, just a note, this is specific to the XRP bot. It's a bit jank how robot container is written, because it's also run in simulation mode, which I'll show in a sec or later on in the webinar. If you were to be using an actual FRC bot, it would be more like driver.x. If you were to set up all the configs dot and then whatever you wanted to do, then it would be the same as this. But another thing to note is on true means once you click the button, it's going to run to completion basically, no matter what. While true, these are your two main options that most commands will use. I'd say 95%. While true is when you hold down a button, when you hold down the button is when the command runs. So yes, it could run to finish, but it could also be interrupted when you release the button. And this would also cause the command to stop running. So that's just something to note. You'll see once we get into commands, it'll make a lot more sense as well. Otherwise, yeah, that's the really high level overview of this file. Another main robot.java, main.java, you shouldn't really have to touch these files. Constants.java, this is where you put a bunch of your constants to kind of keep things organized. We'll also touch more on this soon. The other thing would be almost everything you can see, the two folders here would be subsystem right here. And then, oh, we have an error that just popped up. Oh yeah, because so originally this was 0 and 1. I just had that in for an example. When I first recorded this, actually the audio didn't record, and I just forgot to reset it here. So that's my bad. So yeah, originally this was 0 and 1. But yeah. Next, we are going to go on to, so yeah, you see the subsystems folder. This subsystems are basically going to, we also don't need this right now, sorry. Subsystems is basically going to be where you write all of your methods, and then the commands are where you implement everything and put everything together. Subsystems is kind of what runs in the background. So, and then, so here you can see subsystems, it's going to be the ARM, the drivetrain, the overarching things. Perhaps your claw, your climber, all those overarching things become subsystems, and the specific commands that you'll have in here, you can make them sequences and stuff. So what a subsystem actually is, we're just going to run through this drivetrain files real quick. So here are all of our imports. Once again, this is a really high level run through. You might already know some of this stuff, but just in case, here is all of your imports. And then these first few lines are all going to be conversion factors, basically. So some of this code rather is an XRP template that they provide. So they already have the conversion factors in there. And then I've of course added on a lot of code as well, or some code as well. So these first few lines though, they're conversion factors in order to get from the native units of what the encoder of what the motor thinks of. And then we convert those units into units that we're most used to working with. So units like inches, I think in this case is what I primarily worked with. So yeah, that's what these conversion factors are for. You'll see more on that later. And then here is the range sensor, which is something I added, which is just going to be creating the sensor. And then here's creating the motors. So this is what I mentioned earlier. When you have, like a lot of the times, sometimes if your code isn't working, it's going to be because of CAN or wiring problems where you simply don't have like the right ID for like connected between your robot and your code. And a lot of the times it can be really annoying to look through files and find these. It's because of this that we have the constants file. So we would say like so we could create a new class, at least my team does, where we hold a lot of our constants just so it's really easy to access. I know it's not CAN IDs, but for the XRP on the actual robot, a lot of times it will be. But just for the sake of example, we're just gonna call it CAN now. And then what we do is create a public static final int. We'd say left underscore motor perhaps equals, what's that? 0. Oh, equals 0, and then right equals 1. So then here, all we'd have to do then is come in here and then do can.constants. Or sorry, not can.constants, constants.can. Okay, this tab is acting weird. Sorry about that. Constants.can.left underscore motor. And one thing you have to import constants. One really good trick I like is you can just start typing this out. And then if I just tab right there, it automatically imports for me, which is really, really nice. You can do that for, like if I want to do XRP and like, let's just take this out. For all of these imports, if I run like this, automatically imports. Super, super nice. That's just a quick note. Otherwise, for this, we set this to right_motor. All right. I already see I'm kind of going a bit off schedule. So just another thing you would do for these encoders, you could, I guess, put in the same canting in the constants file, but because their encoders are different, you might create like a public static final class encoder and then keep these encoders like left channel A and left channel B. And for the sake of time, I'm not going to put those examples in constants, but you would kind of do the exact same thing there. Once again, it's not required, but it's a really good organizational tool. All right, so next, this is just creating the drive with the left and right motor, creating a new gyro, accelerometer, and here, range, we create the actual XRP rangefinder. And then here's another key point, set inverted. A lot of the times for your motors, you won't know if it's inverted or not until you actually test it. In this case, the right one happens to be inverted. It makes sense. If left's going one way, right goes the other way. So one has to be inverted for it to be in the correct position. A lot of the times you have to find out if your motor is inverted or not. Like even if you're working with like a climber, intake, even like the intake wheels per se, it just depends on the wiring and such. So that's definitely something to experiment with rather. And then next here you can see this is the conversion to inches, which is what I was talking about earlier, where they use a bunch of their earlier variables here, their conversion factors, to convert from the native units into the units that we most want to use, that we're most familiar with. And then we just reset the encoders. And then after that, we'll go, arcade drive will come back to in a second, since that's the drive mode that's primarily used, or at least in my examples. But here are all of our getters and setters methods. You can see like reset encoders even is just called right there. Here are all of our getter and setter methods that you have for your class that you're going to be using. Same thing here. Really important, it's key for the subsystem, all the stuff in the background that you use in the commands and such. All right, so next is the periodic loop. So this periodic is really important because it runs every 20 milliseconds essentially. And what this means within the subsystem is that things that you want constantly updated is what you want to put in here. So I'm actually going to show you how you might run the XRP bot, even though I can't connect to it because of Wi-Fi. Since I would need to disconnect from the Teams and would stop the recording. I'm still going to show you like the simulate. So we're going to pull that up real quick. I just did a Command-Shift-P, or I guess Control-Shift-P if you're not on Mac, or just if you click this thing, then simulate robot code. And let's go into the sim. So, sorry. Okay, a couple of things to note about the sim. First, right now we're disabled. If you want to run your autonomous, you go to autonomous. If you want to run your teleop, and then you can click your buttons. But yeah, so what you're going to do is drag keyboard 0 right here to joystick 0. If you have an actual joystick to connect as well, then you just make it the joystick. I don't. I find it easiest, of course, to just use the keyboard for the XRP bot at the very least. But if you want to practice for joystick, by all means, that would probably be better. You can practice with robot container with the actual joystick commands. But with that being said, if we're simulating with a computer, we drag that once again there, and then we right-click keyboard 0, we go to the settings, and here we can change a bunch of things. You can see all my button bindings, 1 is Z, like 2 is B, 3 is C, 4 is V, and all the POVs. You can test that, by the way. If I X out, you can see when I click W, my axis 1 is good, S, my axis 1 once again, D is my axis 0, and A is my axis 0 as well, just in the opposite sides. And you can see as I click Z, you can see it light up, C, V, and then B. The order is a bit weird, but that was just for ease of testing for me. Next is network tables, which is right here. You can see distance, which I did the put number there, is right there. These are the network tables, which are extremely helpful, which I will, of course, go into more detail as we get into that. But yeah, that's the really quick high level, like kind of reintroduction, but also good context for how you would actually sim the robot code. So let's head back into Visual Studio and let's take a look at what arcade drive actually is. Take a look at arcade. Oops, what we're going to want is go to definition here. So this is a really good thing. So like arcade drive, this is the WPI and lib, the XRP documentation. You can read through what it all does, which is really, really helpful here. All we need to know basically that we know X is going to be speed and Z is going to be the rotation, which is really important. And then if we go back to like drivetrain, if we say like we want to look at, this is how I also arrived at the units. So let's just go to get distance. And let's go to range. And now if we go to XRP rangefinder, go to definition, you can see I just read through the documentation. I'd rather work in inches rather than meters, which is why I decided to do it this way. So yeah, that is how, if you just go to definition, that's their documentation. It's literally one of the most helpful things like ever. So make sure you keep in mind that you have the ability to do that because it's extremely important. Yep, you can see I chose get distance inches. So with that being said, let's see the actual arcade drive file. We can run through this super quickly. Import statements, command, just creating the drivetrain supplier double, just think of those as doubles basically. And you can see we're just passing it in from what we get and setting those to the values we want them to be. And then, so for the command structure, initialize runs once. Once you first click the button, it's going to run and then doesn't run again. Execute, similar to periodic in the tally up, runs every frame, every 20 milliseconds, give or take. Same thing with is finished. Once is finished returns true, we'll go to the end. So this also runs around once every frame. And then the end is just whatever you want to run like at the end of the command. So with that being said, you can see we kind of just set the speed to what it needs to be. And then here we make an arcade drive where we get in the speed. With that being said, we can kind of see how this would work through these videos. Basic movement, this is just going to be moving the robot as I get smarter. That's the arm that we'll be later, but otherwise I'm sliding back and forth with S and W on the sim. And then here, let's see, these are some basic network tables we can look at really quick. You see, as I'm moving back and forth, just the distance is going to change from the distance sensor. And yeah, just really basic network table stuff. That's just to show it's updating constantly. When I first try to put this in, I put it into not the init or something, or like the subsystem equivalent of init, like up here. Definitely not in the periodic. And I was wondering why my number wasn't updated. That's why it's so important to put that in the periodic so it updates. Another quick thing to note, the reason I use Smart Dashboard, it's the easiest thing you can do. Put number, put boolean, put data, put string, anything you want. You can just use your method. If I didn't want to set like the whole network table structure, so Smart Dashboard is also really easy to use. And it's really convenient, works great. So that's the reasoning for that. Next, we are going to move on to autonomous and like a basic autonomous that the XRP thing provided that I modified slightly. It's going to be autonomous distance. All right. So this is a sequential command group. Okay, first off, they didn't have this when they originally ran it. Sequential command group means one command runs, then the next. Once this one finishes, the next one runs. Once this finishes, the next one runs, etc. until all the commands are finished. It's different from a parallel command group, which is the main other kind, which is that the commands run in tandem. Yeah. So with that being said, we can take a quick look. You can see they create a new, and I'm just looking at time. We're already around 20 minutes in, so I'm not going to, or 19 minutes in. I'm not going to go in depth on each of these turn degrees and drive distance. If you want, XRP has like the template. They have some really good comments in there. You can just look through these files if you want. But yeah, basically they're self-explanatory. Drive for 10 inches at with a half speed, like in the negative with the drivetrain. And then turn 180 degrees at whatever speed and all that. So yeah, it's pretty self-explanatory. If you want to look more into it, you could go for it. But the main idea here is a sequential command group. And what this gave us is this auto. Yeah, you can see each part of the auto here. If we can get back to VSC, drives, turns, drives, turns. So with that being said, what I added on was this, where I wanted the arm to go down after we turned. Say we wanted to grab something after we get there, arm go down, and we can come back up. So auto arm, but this didn't quite work. Let's watch. See the robot's making the turn. The arm comes down, but then it stops and it doesn't do anything. It doesn't finish the other commands. Why is that? This indicates to me right away, I think it's probably because this command never finished. This command never finished, so it can't go to the rest of the sequential command group. That's where we can do some debugging. So here are some network, these are the network tables. I was recording this with my phone, so apologies for the bad quality, but let's look at these network tables that we got our values from and see what's going on with the ARM. If we go to autonomous, we start running, we drag out our network tables. Let's keep an eye on this. You can see, boom, current position 0, desired position -50. So once again, let's take a look at that. Current position 0, desired position -50. So that's obviously a pretty big problem for us. So what I figured out, or what I supposed, is that with the XRP bot, for whatever reason, you can't go past 0. So with that being said, it was trying to go to -50, but we'll see an ARM sequence later, which I can explain. Basically, I'll explain that when we get to it. Maybe, sorry about the order, I probably should have done that first, but it'll make sense. Basically, it never finishes the command is all you need to know. Sorry, let me get into the correct file. Never finishes the command, so it doesn't go to the next sequential command group action, which would be the drive distance. So what we had to do is we change this to, like, say, +50 just for testing. And if we go to the next slide now, auto post debug, let's take a look at what happens. See, it makes the turn. Bring the arm down, and boom, now it's at the correct position and it moves just fine. So this is kind of just an example of debugging with network tables, how helpful it is. You can isolate the problem and it becomes so much easier to fix. You can test so many different variables at once, or I guess you would want to test them individually, but you can see all the variables in the network tables. And it's extremely helpful. That's an example of a debug that you might have to do that I specifically had to do in this case. So with that being said, that's kind of the autonomous. Obviously, it's not really that much in depth into autonomous. Part of it was also just introducing sequential command groups. But this next part is extremely important because the ARM, the servo, I think it's such a good example. It's a really oversimplified version, but it's so similar to actual FRC coding, and I can tell you that from experience. So I think this is such a good example here. So really make sure we're paying attention to this. So we're just going to run through the subsystem first on the ARM. Let me make sure on the slideshow. That is the next thing, right? Yeah. All right. So imports, and then create the ARM. And here we have a double desired angle. Here we just create the ARM servo. Once again, you could put this into constants, but in the interest of time, I'm going to keep going. Usually you would want to put this in constants, in fact, but yeah. Next, periodic. Once again, every 20 milliseconds, we want to put our number, we get our desired position. So what it's going to be named in the network table, and then the variable you're getting it from, desired angle in this case, get angle and at angle. Keep in mind, this is a Boolean. All right. Next, also you can see here the comment 0 to 180 degrees is what the actual angle can be, which once again makes sense with why the -50 didn't work. So here we have 3 really basic methods, but this just shows like set angle, and here's where we use desired angle because we want to keep track of where we're trying to go. The reason we want to do this is once we get to the set position, we might want to perform another action. That's why we have at angle here. If the get angle up here, if m_armserver.get angle, which actually this can just be get angle since we have it right there. So if get angle, which we'll just call this, is equal to the desired angle, then return true. We're at the angle we want to be, the angle we're commanding. Otherwise, return false. This is going to be really helpful. So once again, this is such an oversimplified version because it's literally just this servo. Such an oversimplified version of the XRP oven like subsystem, but it's also such a good example because it's so similar to like what actually happens. Next, arm sequence is an example command. Here we're just creating everything. Angle done, count, and finish count. So this is going to be like the delay. This is how we create a delay, which you'll see in a sec. So the main constructor that we'll use for some reason, if you need the drivetrain, that one's there. But the main one we're going to use is this constructor, which we just take the arm and the angle that we want to go to. So first on initialize, this is extremely important. You set done to false and count to 0. You can see return done is finished. If I don't set done to false in the initialize, what this means is that the first time I run this command, yes, if I set like done equals false up here, I took it out down here. Yes, the first time I run the command, it's going to work just fine, perfectly. But then it's going to already be false. Only in the initialize is it called again. So that's why it's so crucial to set this in the init. Otherwise, first time command's going to run perfectly. Second time without redeploying the robot, nothing's going to happen because it'll call is finished right away. Same thing with account or similar thing. And then we set the arm angle to the angle we want to go to. So that's kind of the point of the command. We feel comfortable doing that right away. Next, in the execute, once again, this runs every frame. So I'm saying if arm.atAngle count plus plus. So this count equals 0. And then if once the count is greater than the finish count, done equals true. So this is basically saying after we reach our desired position, we wait for X amount of frames, finish underscore count amount of frames, in this case 100 frames, and then we set done equal to true. So then we come to here, return done, and then we set the angle to 0 at the end. Whether you actually want to set the angle to 0 at the end, not sure if that's a possibility you want to do, but obviously you can do whatever you want at the end of the command. So yeah, that's the delay. So let's see this in action. I think at first for the first video, this was actually around 5. So let's just see this. See, delay very short, just comes up, comes down. Now, if we were to change this to 100, let's see the delay this time around. See, much longer stays there, and then it comes down. And that's just also shorter. We'll see. You'll see what that means, but you can see much longer delay when we change the frames, just how many frames it work. And each frame is around 20 milliseconds for reference, I think, give or take. Yeah. So that being said, that's just the arm delay. And next, we're going to show you the network table. This is just at angle. So here, the reason the current position is 90 and the desired position is 0, I just booted off the XRP. And it's like desired position is always 0, current's 90, but since there's nothing commanded to go to the desired, it's just how it shows up. But what this shows is our at position is working. It is indeed false. And then when we click the command, boom, we're at the correct position we want, desired position, and our at position is true. So yeah, that's all good. Clarifies that our network tables are indeed working. All right, so next is going to be the distance demo, but before we get into that, I just wanted to show you here in robot container, you can see here we did on true, went to angle 50, and on true went to angle 5. Those are the different, that's accounts for why we go to 50, 1 to 5, just to show the different angles that we can go to that we're passing in as a parameter. All right, wonderful. Next, we can go onto the distance sensor. So distance sensor is created in here. It's or rangefinder range, I guess. And you can see once again, I'll just go over this briefly. Get distance, I get it in inches, and I update it in the smart dash, in the network tables rather. The key thing here is going to be this file called drive sensor, another command. So arm, obviously this is all good. Final double finish count, all this boolean done double count. This is great. Yeah. So what we're gonna do is create a new drive sensor. Here, these are all variables. You will see what each of these are used for. We have arm and drive. Keep that in mind. You can have multiple. And then initialize once again, done equals full, count equals 0, false rather, sorry, same things. And then here we're saying on execute every 20 milliseconds, if our distance, which we're passing in as a parameter, if this distance is greater than drive.getDistance, the distance detected by this sensor, the distance sensor or range sensor. If distance, which let's say is 10, is greater than the distance we are away from something, then we set the angle. So once we get close enough, then we set the arm angle to like 80 in case it's like a task or something. We want to automate that. And then this is a while true command. This means is finished can always return false, since interrupted will be the one that causes end to call. We set the angle to 0. And let's see this in action. So you can see our distance sensor, the thing we're detecting is going to be the wall right there. See, now we can go up. Before, when we're outside 10 inches, we can't move it. We have the option to go up, and now we're back here. Once again, we can't move the arm up and down. I'm clicking the button, but it doesn't work. Let's watch this in full screen here. So I'm clicking the button, even right here, I'm clicking to try to create a new command to move it up, but it doesn't move up. But then once I get here, still doesn't, not close enough, not close enough, close enough. Now I can move my command. And then once again, Back here, I'm clicking, but it doesn't move because of that command where we require the distance. So let's look at what the network tables look like while this is happening. Take a peek. Distance, I'm clicking the button once again. I'm clicking the key. I'm trying to move the arm. It doesn't work because our distance is greater than 10. Still doesn't work. And there, well, as soon as we hit the 9, you can see, oh, sorry, it's already changing. It changes to 80 and it oscillates between 9 and 10, but now we get closer. Now we're hitting the current position. Now we're hitting the desired position that we want once we get within 10 inches there. And just to clarify here, robot container, it is indeed 10 inches right here. So that's how that works with the distance sensor. That's just another example of the command that you can write. Once again, I think those last 3 files I went over are extremely important. arm.java, drive sensor.java, and arm sequence.java. It's actually so similar to an actual FRC subsystem in our commands, which is why this XRP bot is so good as an introduction, because it's so similar. Obviously, it's so oversimplified, but it's really similar. And if you can get a good hang of this with good experience, you can definitely get into FRC programming really, really pretty quickly. It's really pretty amazing. All right. So with that being said, in just over 30 minutes, that covers most of the main stuff related to the actual programming. I know it was a really pretty quick and broad level overview. That's kind of the overview. So with that being said, we are going to discuss potential next steps. So how to practice. Let's go over the release repo and stuff. So if we go here, if we go to the reference links, we can see the base release GitHub. So if I go to this just to demonstrate, this base release is basically just the XRP like demo example template. I didn't add any of this stuff. Like none of the stuff I added is in there. So as like lesser methods doesn't have the rangefinder sensor, doesn't have as many network tables, all that stuff. What it does have is it allows you to drive the robot, allows you to move the basic servo. That's it. But it's a really good place to start. If you were to start, like you could download the source code file and then the zip, you'd have all the files in there. But if once you unzipped, of course. But what this would allow you to do is essentially like practice. You can try to replicate kind of what I did and go even further beyond. So you can have the basic code and then try to replicate what I did, create those same subsystems. That could be one of the most helpful things you can do. The second release GitHub, which will be posted soon once I finalize the release and I send it out, which it should be by the time this YouTube video is up, the link should be here. Second release GitHub, if you were to go above and beyond, if you thought you could add another motor, another servo, another sensor, something of the sort like that, then I would recommend using the second release GitHub and instead using the code from there and really go above and beyond. But if you're to do this, really make sure you understand both the base code and the code that I've added on. Otherwise, here's some other referencing to the first YouTube video. The second one will be posted around the time that this actual video is posted out, and I have the link. And then if you want to clean things to this slideshow as a whole, it's tinyurl.com/xrp-demo-wi. So let's go back to next steps. Release repo, so that's the base once again. And if you wanted to like find this, you could also find it's on my GitHub. The repository. So another thing to practice, if you really want to get like the best practice, I would say literally start with nothing. Maybe just start with just the conversion factors that's given to you, like literally just the conversion file factors, and then try to, if you're able to program from scratch up to where this is now, you're going to be in an extremely good position to program to contribute to your team. That would be very challenging. That would be, if you're up for that challenge, you would definitely be ready to be a good contributor to your software team in FRC. If you're able to like completely build this out from scratch. So if you're looking for a challenge, that's what I would recommend. Otherwise, if you wanted to go further, you could add motors, add sensors. One thing you can do as well is if we look here, this is just a way I like to see like all the different libraries, especially for XRP, which I'm not too familiar with. You can see gyro motor, but like this reflectance sensor, if you wanted to work that reflectance sensor, you could try to work that out and try to create some commands with the reflectance sensor. That could be some really good practice that you could do if you wanted as well. Otherwise, you can create different tasks and commands as well with this XRP bot as next steps. Otherwise, if you have any questions or comments or anything, feel free to comment it on the YouTube video, or I should also, as a reference link, the best way to contact me. Oh, I should have this. Email would be noah@firstinspireswisconsin.org. So if you had any questions, comments, concerns, anything of this related sorts, please don't hesitate to email me here or comment on the YouTube video. If you have anything that you would want me to go over, create maybe a shorter webinar, shorter video in the future, such as going over the reflectance sensor. Obviously, that would be much shorter, maybe 5 to 15 minutes. I would need to look more into that. Then you could let me know for that, and I'd be more than happy to do that, or any other questions you have related to this. YouTube comments, or shoot me an email and I'll be sure to get back to you. Another thing to note, yeah, a big reason I only went over the range sensor was to give you an idea of how it works, but also give you the opportunity to go and play around with these new sensors and kind of explore on your own. So yeah, with that being said, those are things you can look forward to in the future. Otherwise, I hope that this webinar helped you, and I wish you all the very best of luck on, let me stop sharing my screen, and I wish every single one of you the very best of luck on your upcoming FRC season, for your FRC teams. If you're currently in the season, the best of luck to you as well. And once again, thank you everybody for watching. I hope this helped you and your team. And with that being said, thank you everyone and have a great day.